runs one of the biggest groups, research groups in Europe on the quantum simulation. And I'm very much pleased to have Enrique today. Let's give him a big round of applause.
So, first of all, thanks, Andre. I really appreciated also your presence in the conference in SETI in Mountain View some weeks ago, and your questions and your interest and the invitation for coming here. And for me, this name of Hacker Dojo and these improvised conversations are exactly the motivation why I'm here with my wife and with a researcher from my group. Just to give my talk, I would need to connect my computer. So we just do it. That's right. It is here from Cupertino Technology, so.
This is Mountain View. There's no telling.
Okay. And I mean, it was very hard for me to prepare something, not knowing very much the audience. But after these conversations, I think I will switch topics.
And I see at least 3 physicists in the room.
Oh, okay. You scared me. Okay. I should assume that you know something about quantum mechanics?
No. I don't know about other people.
Or not? Just
one more physicist.
Go ahead.
Physicist?
Undergraduate. Anybody knows.
Undergraduate in physics. In quantum.
I just graduated, just physics.
Correct. Well, but you didn't use quantum.
Software?
I'm a computer engineer.
Okay.
Go ahead and do your original
Okay.
presentation.
You read it already. You found the mistakes now. Okay. So great. The first thing, please ask questions, interrupt politely. I always say politely because some people get excited. And of course, I don't mind just cutting by half my talk as long as I get your feedback and we can discuss about it. I really want to transfer and to receive more than just to make a talk. It's a little boring to speak to myself. Huh? As I always say, the mirror at home is enough. And it's a little boring sometimes. Yeah. Fine. So the title of my talk is already there, not yet.
No, not. Yeah, it should be working.
Just play it again.
Oh no.
You had it for a second there.
Wow, great.
Yay.
Wow. It is smaller than my screen, but that's fine.
No.
So the title is of course a provocative one, but I really mean it. If you heard something in SETI, or if you got something in SETI, it's really that. The kind description of our group in Bilbao, Spain, given by Andre, I don't know if it's because of the number of people that is just increasing or by the quality, but better not to answer, and this is for the dinner time. We do research in many topics around quantum, as you see. At the beginning, I started with quantum optics, but we jumped from topics based on an open-minded approach to research that we have. That is literally as I described in talks. Is we wake up one day, we have an idea, it's crazy, we check and we don't have the know-how, we look for the experts and we work on it. See? So I know that there are some experts here in 1,000 topics. Let me tell you, at least for the younger, 21st century is not the time for encyclopedic research. It's a time for creative research. And from this point of view, ideas are appreciated, interdisciplinary ideas, and the best encyclopedia, of course, is Wikipedia, and colleagues, and traveling. No? Now with airplanes, internet, and everything, it's rather easy to get in touch. Of course, you have to dare to go for them, and that's the way we do research. As you see, the last topic in this list at the middle is quantum biomimetics that we are developing with Mikel, which is as crazy as taking the studying what are the characteristic behaviors of living objects and try to propose them as building blocks for quantum behaviors of dead matter. No? So we are trying to connect behaviors that are associated with living systems and to reproduce them artificially in what we call dead matter or atoms or photons or these kind of things. I will not say anything about it. I just wanted to convince you that we are crazy enough to work in many
This
topics.
is
and to
even
combine.
crazier.
That's right.
than what we do.
That's right. That's right. It's crazy that making possible physics. With Mikkel yesterday, we were discussing in Berkeley with colleagues that work in artificial intelligence is pretty impressive. But so I will try to advance. I don't want to disappoint you in the sense that I would want at least that you get the issue of the title of the talk, in the sense that in Bilbao, in our group, we have been leading, we have been proposing pioneer ideas on how to convince atoms and photons to imitate behaviors that are forbidden by the fundamental laws of nature. Okay, so this will be my goal. If at the end you say, I didn't get it, then we start again. so you have to lie at least if you want to see today. So essentially is simplifying the two fundamental laws or theories, if you want. Quantum mechanics, relativity. Simplifying without entering into any details. Two fundamental things. There are laws and behaviors there that cannot be broken. One example, causality. I think here in US you call it soccer. I don't know the slang for basketball. But let's say in soccer, you cannot make a goal if you have not shot the ball before, right? So what we are doing is that nature behaves as if it contradicts this principle of causality. So this is, for example, one of the examples. And there are other properties in quantum physics, like, for example, time reversal processes or complex conjugation, that is a mathematical operation, that are just forbidden. Quantum mechanics forbids that you use a wave function, that is just a mathematical function, and then you apply a complex conjugation. Such a simple thing, you know what is complex conjugation, right? In a complex, you write the function, you apply complex conjugation with your hands or in your computer or in MATLAB, and you say, I can do it. An atom cannot do it. A photon cannot do it. The wave function describing quantum systems cannot see this operation. And we have created this research line that we called quantum simulation of forbidden operations or of impossible physics. And I will give you some examples, among several others, to convince you that these crazy things is just physical. And why the name quantum theater? Because I do believe that quantum simulations or quantum imitations, I like to call it, are strictly associated to arts and to aesthetics, to the concept of standing up in front of an audience and to fake behaviors. Like when you go to the theater and you go to the cinema, you see movements in science fiction or happenings that you say, this contradicts, this cannot happen. But you want to believe it, first because you pay your money, no? And second because that's why you go to the cinema, to see fiction, to see something that is just strange. Right? Now we have developed the concept of quantum theater in the sense that we go to the atoms that are not living objects, or to the photons, and we tell them, please dance, sing, and behave in such a way that you contradict your internal fundamentals. And that's the essence of the quantum theater of impossible physics, and I hope I reach the end of the slides so that you get it. You find it crazy enough? Okay, great. So this, I mean, in Silicon Valley, it's very hard for me to give introductions and definitions, because here you have heard everything, right? But this quantum stuff, quantum computing, quantum simulations, started with this effort of merging the fundamentals of quantum physics with information science. So here, for me, I'm not a humble person, but I come here and I go, we just came from the Computer History Museum. You see, it's really passionate, all what has happened in this area. I'm really impressed. No? I come here like a baby to check my first computer years ago. But this merge has produced crazy ideas, simplifying for the people that are not experts. The key difference between it's not to beat me. Okay, fine.
Not yet.
Not yet.
Not yet.
Not yet. That's right. Wow. The key issue about the difference between what can be called a classical computer and a quantum computer is the transition from the bit to the quantum bit. And what is this difference? That first of all, you need a physical register. You see, mathematics is a construct of the mind that just is cheating us, because sometimes it convinces that it exists, this Platonic world where mathematics exists. No? Each time you think in mathematics, you are already assigning to the mathematical objects a physical register. Right? So when we say bit, we really mean a physical register. It can be whatever, a box where you put an apple or you don't put an apple. This is the 0 and 1. But it will be very hard to convince you that in a box, a physical register, you can put an apple and not put an apple at the same time. Okay? This is what happens in quantum physics with the quantum bit, that an atom can be in the ground state or in the first excited state at the quantum level at the same time in different superpositions. And not to lie to the audience, because the dissemination MOOCs and the popularizing talks are full of mistakes. It's not as people think that it's just a statistical issue in a simple manner, because classical statistics allows that you have probability. The probability of having is 0.5 or 0.8 is not as simple as a classical probability. This probability coming from quantum mechanics is much more subtle. It's not the moment to tell you the details, but it's just much more subtle than just the probability. Okay? But this is more or less the essence. Quantum information, this merge in the 20th century, late 20th century, has this access. Quantum computing, I will not say much. The only thing I like to say when I mention quantum computing is that I think that it's stuck waiting for several breakthroughs to succeed. See? The symbol of the quantum computer is a scalable short algorithm for factorizing numbers with many digits that requires, in the most optimistic cases, several dozens of millions of qubits, when at this very moment nobody can manipulate under total computing control more than 5, 8, 10, depends on your technology. If you tell me, what about D-Wave? Then we have to prepare for the talk. We know everything about it. That's right. Because cultural issues, you go to Europe, honestly, you say D-Wave is like, you see like you are coursing somebody. So this is not quantum at all. Yeah? So there is a huge debate in Canada. We have to change. You see our style of speaking is very subtle. But anyway, that's an interesting topic. Quantum metrology is the possibility of using the quantum for making higher precision measurements. Also is an interesting topic, very applied. Quantum communication is in the industry. I've not heard many industries in US, but I know several in Switzerland, in Australia, in Europe. There are several enterprises that are already making money selling with honest devices. That just that you know, because I see that you have very good contact with the industry. They are not very good quantum cryptographic systems. So we know it, but people are able to sell it just because it is fun. And of course, who buys are banks, Swiss banks, and then things work. So they are using the most primitive cryptographic systems.
Yeah.
But
there's a YouTube by this Russian guy on how to hack quantum crypto.
Yeah, that's right. Yeah, but this Russian guy is hacking quantum cryptography of the true fundamental methods and also some applications. But as I said, it's the fashion of buying this. In fact, there were elections in Switzerland. People were using to send some results from one city to the other. We all know that we can break all that cryptography. But it's the time where people are just making money. If you are young and want to make good research, I don't encourage you to work on quantum cryptography. I think it's getting boring. It's in the moment of many applications, many subtle things. The key issue in the quantum, just solve the problem of scalable quantum computing, that would be great. But for young people, this is perhaps too much to ask. And I always say, perhaps because also we work in that, but we work in that because we do believe, what I'm going to say, is inside quantum information, we are living the times of boosting this using fundamental physics, using applications, using devices, using creating some small enterprises. So it's the next 5 to 10 years we will see the explosion of this field. It's the moment of where you can have everything, your creativity, your interest for funding, for money, for applications, for enterprise, for fundamentals, is the right place to work when you need all these things. This definition of quantum simulation is very important. I can send you the PDF, Andre, if somebody wants just this later. is this intentional reproduction of classical or classical aspects of physical or unphysical models into quantum or classical aspects of another quantum system. It's too technical for you, but I'm sure you will appreciate if I give you some explanations. Usually, when you simulate models, we tend to say we use, for example, the structure of this bag, and we try to imitate this bag into this other bag, just to give an example, imitate. But in fact, we never imitate objects. We imitate features, we imitate aspects, partial aspects. It's always partial. See, when you say, for example, I use a hydrogen atom, and I want in the hydrogen atom, I want to imitate a helium atom, just to get a little bit far from the uranium. You see, imitation. We don't imitate matter. We don't imitate the full structure of systems. We always take partial behaviors. Imitation is always about partial behaviors, and I will insist on that. So formally, simplifying, I hope you get it, because it's quite simple but quite deep. We humans use our intelligence to observe. We observe. We try to describe. We make abstractions. When we make abstractions, we go to this Platonic world, to the cloud of our minds. This is the way we do. And then we make models. Then we are back and check. I can predict. It fails. I have to change again. I come back. I predict. Oh, it works. It works here too. I have a theory. I am there. Have a theory. When I take this model, that is always partial, of course. We don't have access to reality. Whoever says that have access to reality is a religious person. It's not a scientist. Okay? This is my opinion. Sorry. Okay? We make this model. When we want to reproduce that model in a completely different system, then we are doing an imitation. This is what we call a simulation, an imitation, an emulation, and in our case, we put the quantum in. Okay? We put the quantum. That's our job. Yeah.
So, since you're speaking very platonically, what are you going to say about this abstract realm that you're using to construct your models? Is that reality itself?
Not.
Because I mean, when you get down to the physical world, then you would agree with Plato if you said that this is sort of imitation.
I didn't want to enter into that because you are fully right. But I will not run from giving you a formal answer. When I say that we go from the observation of what we call reality, I don't care about reality. I care about the observation, the interaction. This is what I care, because it's the only thing that I can observe. And I make a model. The model does not exist out of the nature. It exists in. And it's again, it's a reality that is modeled by myself. See?
I was just curious where you stood, because if you read a book like Roger Penrose's Emperor's New Mind, he comes out very strongly in the first or second chapter.
I said before that my stuff is about science and not about religion. So,
okay.
So when you measure,
I just want to know where you stand, and now I know.
Now you know where I am. You see, so I will tell you even something more that we can discuss later. For me, Einstein was the last great mind that was making science with a religious approach. See, his negation to quantum physics was based only on his taste about nature, which is not our job. Our job as scientists is to describe what we observe, not to impose our prejudices on our models. Okay?
On the other hand, some very great discoveries were made by someone feeling nature must be a certain way. I don't think the theory of relativity.
I never said that religious people cannot produce great science.
Because Einstein himself came up with relativity, thinking.
That's right. That's right.
And Dirac discovered the positron.
I'm not judging or saying anything against. I'm just saying that this is not our job. You see, I produce great physics having a shower.
Was it Lemaitre who was the Catholic priest? Lemaitre, I think, was the Catholic priest.
Yeah, no, I have nothing. I mean, I'm not religious, but I have nothing. I'm just saying that our job is to describe. If you forgetting the intuition, forgetting a better description, you need to dance and to think that it will rain because you dance. Dance, man. This is of course I tell my students, do whatever you need for create, because the goal is to describe. At the end, what matters to me is to describe. The way you get the description, I don't mind. The inspiration comes from completely hearing music, playing football. It's not no way. Okay? So at the origin of this, and I wanted to again to make a historic approach in my talk. Richard Feynman in 1982, after a talk, wrote a nice paper. If you have a look to that paper, he speaks about quantum computing and quantum simulations on the same footing. For him, there was not much difference. Nowadays, for us, for the experts, you will see that people say, no, I do quantum computing, no, I do quantum simulation, no, I do analog quantum simulation, I do digital, no, I only go short algorithms, no, I go global algorithms. So this is boring, it's wrong, misleading. It's just because you need to explain what you are doing. But things are gathered. There is not much difference at the very beginning, because the goal was just to use the exponential growth of the Hilbert space dimension associated to the wave functions of quantum physics to calculate for us, as Feynman said. I don't know how familiar you are with the mathematics behind quantum physics, but formally the reason why it is so crazy and people are looking for designing quantum computers is because there are very, very simple problems, you see, as the factorization problems and others, or trying to compute things of quantum mechanical systems that require, for these classical computers, are just impossible. If you want to give one example, knowing more or less your background, is rather easy. One of the key features of an electron is the magnetic spin. No? It's a two-level system for quantum mechanics, just two-dimensional system. If you put 100 spins, 100 electrons, the dimension is 2 times 2 times 2, 100 times, 2 to the 100. Quantum mechanics requires to associate to the quantum state of that system a vector with so many entries as 2 to the 100. Then if you tell a PhD student to write just in any classical computer 2 to the 100 complex numbers, just this is impossible. Imagine to compute on that. You see? So just 100 electrons, and electrons have charge, kinematics. I'm just saying the internal degree of freedom called magnetic spin, and we cannot compute anything with 100. Then if I tell you a material, you know how many electrons have a material? Of the order of the Avogadro number, that means 10 to the 23. So you can imagine now, if I tell you, just use a spin, don't describe it, just a spin, it's 2 to the 10 to the 23. This is more than the number of particles in the universe, and this is just impossible to compute. So, Feynman, yeah?
Well, they're not fully entangled. So
Sorry?
It's different, isn't it different because if they're fully entangled, then you get the full exponential?
Can you prove that this is fully entangled or not? But that's a key issue. You see, I could not even dare to ask this question, because nobody can answer. If I tell you if it is white or if it has some colors, what is the texture, is it elastic or not, I can make tests. Anybody saying if it is entangled or not is just hand waving. There is no way. See, people are making the world records checking entanglement for 4 particles, 3 particles, 10 to the 23. This is a question that nobody asks. If somebody says something, it's just guessing. And it's very easy because nobody can prove him wrong. So this is the issue about quantum mechanics. You see, complexity comes just from the number of particles and the dimensionality that grows exponentially. Feynman had this brilliant idea to say, we will never be able to reduce these to algorithms done by classical computers. So what we should do, we should use the quantum theater. What is the quantum theater? Instead of trying to pass the complexity of quantum mechanics to the complexity of classical physics in this manner, we just use another quantum system that tries to imitate the first, the same structure, the same dynamics, the same dimensionality, and we can ask questions like that. See, you use controllable systems, controllable quantum systems to imitate inaccessible complex quantum systems. See? But this is the fundamentals. There is much more, and we will tell you what are the novelties. See? So I will tell you really what are the last steps into these efforts of implementing the quantum theater. Okay? And I like the association to the theater because when I was in Athens with my wife, for good reasons, I started to study. If you check Aristotle and other philosophers 5 centuries before Christ, they were not only creating theater, but they were writing the theory of what should be called theater. And they said, what is the definition of imitation? What imitation is about? And when you read it, you see that we have not invented anything. Everything that is in quantum simulation has these components of the theory of imitation, only that with the quantum in front. So that was a very, very important for me step, because sometimes we work so close, we are so in a hurry, we believe that we are discovering the world. And it's very shocking that some people 25 centuries ago was already making this theory. And at this very moment, if you ask an expert, give me a definition of quantum simulation, and what is the difference between quantum simulation and quantum emulation? Total silence. You see? I will raise this issue in my talk.
So who introduced this idea of the quantum theater, or that term? That's you? Okay.
Sorry. To deceive you. This is, I introduced. And to close the metaphysics, I will tell you, I will share with you another of my claims, you see, because this I cannot prove, this is not science, these are just statements, is this conjecture on the origin of creativity, see. First, I claim that imitation or simulation at the classical or quantum level, before art or science, is just impossible, is condemned to imperfection. This is a statement coming from me reading about painting, music, literature, poetry, sculpture, cinema, quantum physics. See? I claim that man, humankind, has tried to imitate as much as possible for art, for science also, you try to imitate objects, no? And this is frustrating, because you never reach the perfection. I claim that it's just impossible by fundamental principles. I cannot prove it. It's not a science.
So I do have to protest a little bit here. That's you know, this idea that art is imitation. I mean, that's a theory put forth by Aristotle. You know, this is an Aristotelian theory, which in which he's trying to come up with a theory of art and what it is. And Plato talks about imitation as well. But the problem I have with that is these are people who, are coming after the fact. Now, if you ask a great artist, I mean, you listen to something by Beethoven, for example, his Ninth Symphony. I would ask the question: how is that an imitation, and in what respect is it imperfect? Is it, it's less perfect than what? What are you going to compare it to? So, I mean, I think, since you brought this on yourself by being very expansive,
that's right.
Going into the arts, I think it's fair to ask the question.
I will not finish my talk, but I think
I'm just saying I'm just having trouble with that statement.
That's fine. I will be more precise.
I think you should add quantum metaphysics.
I do, but then I would want to end up with the physics too. But I don't want to run from this discussion because I'm reflecting on this.
He's got that chair over there ready.
I am reflecting on this sincerely.
That's a special
It's very hard that I get a question that I have not thought before. First of all, I am of course making a description of the effort of the humankind in science and arts to imitate as close as possible to the original object. The first sounds try to imitate probably birds, right? So this is the origin of Beethoven, of Mozart, if you want. I'm not claiming that Mozart, the Zauberflöte or Beethoven Fifth Symphony is an effort of imitating, not necessarily. Even though if you check the history of how Beethoven created that, was hearing birds. So have a look to that. The ninth, the chorale, here, carefully. This is the main melody. He said, "I am copying birds." So, but I don't want to enter into this debate, but he was trying. But my point is that by trying to copy, and we were visiting Stanford, in one of the main areas, there is 6 figures of Rodin. Rodin was accused, in fact, in the academy, of saying he's destroying art, because he was able to produce a human body that was perfect. All the experts in his time said, that cannot be art, this guy is cheating. He has taken a human being, he has put some object, because he's so perfect that he cannot be. So in the history of humankind, we tried to imitate, and we failed frequently. I'm not saying that this is the only thing we did. In fact, if you read the second part, what I'm claiming is that we started, you see, in the moment where the father of a family or the mother of a family said, "We are too many children," and said, 10, I don't have more, 20. Took stones and said 25. These are symbols. Each stone is not a son, it's not a daughter. Each stone is a symbol of what? Of the abstraction of a unit. You see? So this is what I mean. The origin of mathematics, in my opinion, comes from imitation, from symbols. So a stone is a human being? No, it's just a symbol of the unit. That's what I mean partial imitation. So when you say, I have 25 sons, I don't mean that each son is a human being. It's just, you just need to count to see if they are lost or not, and then you imitate. But it's a deep discussion that you raised, and as I said, we can discuss hours with this. But I really meant that. We try to imitate, we fail, we get frustration. The frustration inspires, and when we get frustrated, we create. See, this is the way we work in Bilbao in our group. This is the way we work. We think in art, we think in imitating, we fail, we create those things. Okay? So that's more or less I wanted to share in this direction, and of course this gives for a lot of discussions concerning music, painting, and many other things. Huh? Now, coming back to start to be a little technical, the first example I wanted to give you, I don't know if I can erase those wonderful circuits there, but at any moment I can do, you see? So you can now pick me, Prof. So let's say wave function, see? It's a function of some variables, if you want, of position and time, and I am just speaking about this complex conjugation operation, you see? Typically people represent it with K, see? You apply this function, this operation K to this wave function, and you get a complex conjugation. If you see carefully, I have done it. I said before that it is forbidden, but I have done it. I have applied this to psi and I have written that. So if you don't believe me, you can write 2 plus I3, and I put 2 minus I3. So I have done it. Then why I claim that it was impossible? Can you tell me?
I don't get it.
That's right.
Because black lines on the white thing are not a quantum state.
That's right. So I'm saying just that I don't know if you're familiar with complex numbers.
Well, please. Okay. You know, quantum mechanics is formulated with this idea that states are represented by Hilbert vectors.
That's right.
And part of the definition of Hilbert vectors is that they have a dual. Okay, and that you can form an inner product with that dual.
That's right.
This idea of, you know, imagining that you have an operator that transforms a vector into its dual. I mean, to me that's puzzling because you know it's a definition of Hilbert space that for every vector you have a dual, which is represented by the complex conjugate.
That's
so when I say I don't get it, I'm just saying I don't understand what you're trying to accomplish.
No, that you described it correctly. This
Okay.
what you described is
Complex conjugate comes from the fact that you need positive result when you multiply.
I know,
no,
what I'm saying
no,
is
I am fine. I like that you described like this. This what you described is impossible.
what's impossible?
Nature cannot do this operation. You see, when I gave this talk in Yale, Michel de Borré also raised a hand and made the same objection. I had to offend him respectfully. This is
You don't have to be as respectful
no,
to me
but
because
I
I
know,
know
but I mean, you open any textbook in quantum mechanics and you will see that quantum mechanics is about unitary linear operations. Complex conjugation is an anti-linear non-unitary operation, as simple as that.
Enrique, I have actually a different problem with us speaking about complex conjugation. Because we have a complex Hilbert space, there are many different bases, and the complex conjugation depends on which base they have chosen.
That's right. That's right. So
So it's not unique operation for a given Hilbert
as
space.
I said, I am here to have this kind of questions, and I can stop here if we need to be precise. But I'm sorry to tell you that just a complex operation is a problem. Where is the mistake that people do, and even as I said, even experts sometimes that are not familiar with this is really ABC. It can be in the first page of any elementary book in quantum mechanics. It's just that we are confused by what we can calculate on papers and on classical computers and what nature can do quantum mechanically.
Right.
Which is a typical mistake. That's why I'm so proud to have created this field of simulating possible physics. Because I myself had to learn these basic things. Not everything that we can calculate, nature can do, at least at the quantum mechanical level.
So really what I'm getting at is, what do you mean by forbidden? Are you just meaning that there's no natural process that you can associate?
I give you the example I gave to Michel and to many colleagues that asked me about it. Experts in quantum mechanics asked me this question. We were speaking about superconducting qubits, for example, D-wave, take a flux qubit, describe
Whatever that
a two-level system quantum mechanically, and I keep it here. Of course, I need cryogenics, 10 millikelvin, accept the game, the Duncan experiment invented by Einstein. See? Have a wave function describing it. I give it to you, and I tell you, apply the complex conjugation. You can pass the age of the universe. This is impossible. Quantum mechanics has certain fundamental laws. One of the fundamental laws is that any operation that acts on a wave function has to be described by a unitary operation. A unitary operation is not the complex conjugation.
Okay, now that's all I wanted. All I wanted was what you meant by forbidden. Now I get it.
That's what I mean. Another forbidden thing that is of course more evident. The complex conjugation is more subtle because I agree. You have read books. Everybody makes complex conjugation. I did it. That's what I wanted to provoke. I did it, but I did it on a classical register that is the whiteboard.
On a certain basis.
Exactly, and in a certain basis. But when I tell I have a wave function that nobody knows is encoded in a physical system,
Right.
this is a forbidden operation. This is a subtle difference. It's deep, it's confusing, yes. It doesn't happen at the classical level, it happens at the quantum level. Okay? I will tell you another example that I will not develop in my talk, and it is causality. Causality is more evident. So you cannot make a goal. How do you call it in basketball this dunk?
Basket.
No, this,
Slam dunk.
that's right, slam dunk before throwing the ball, right? Or before jumping. So this is breaking causality. Also, this everybody agrees that it's a forbidden operation. You see, you cannot have the cause, you cannot have the effect before causing it. See, this is a basic thing in nature. We know also, we have one of the papers, of the 3 papers I mentioned that you put in the website, is doing that. It's showing how atoms and photons can imitate non-causal behavior. So how photons and atoms can make goals before shooting the ball. Of course, this is an absurd. Causality is a fundamental principle. It turns out that complex conjugation is also a forbidden operation, like breaking causality. And then why also some colleagues have some overreactions when I talk about this, because they are not getting that what I'm telling you is about cinema, about a movie, about theater. And when you see Spider-Man violating the fundamental laws of Newton, you are not saying, that's wrong, come on, this is, I am getting crazy. No, you know that it is fake, it's theater, it's imitation. We are doing the same, we are bringing theater imitation of absurd behavior, imitation, not reality, imitation to quantum stuff. Yeah? Anyway, I will be back if you want for technical things. Graphene, I don't know how familiar you are with graphene, but I can overlook this. In graphene is a material, there is a Nobel Prize a few years ago, and in graphene, the description of graphene is associated, funnily enough, with the Dirac equation. This is technical, and anybody who wants details, you just let me know. But you see, graphene is a material, it's a non-relativistic system. However, if you check the quantum description of graphene, it's associated to the Dirac equation that has relativistic covariance. I don't call this a quantum simulator because there is no purpose to use the graphene as an imitation of relativistic behavior. However, you could find it there. And as I said, I don't want to say much because I know pretty well what are my goals now for the talk. See? So now I will start to argue what are the purposes or the relevance of quantum simulations. So the first one, as you can imagine from what I said before, is a fundamental one. You see, quantum simulations or classical simulations or any effort for imitating has as a main goal to connect different fields. The example I gave there is done by some colleagues some years ago, where they discovered that the BEC, this Bose-Einstein condensate, that was also assigned a Nobel Prize, just can reproduce artificially the behavior of black hole physics. So there is nothing between BEC and black holes. Black holes described by general relativity. You have the famous Hawking radiation. BEC is just one, people call it the new state of matter, was predicted by Bose and Einstein and so on. You do it in the lab, you have to cool down, the cooling techniques. It's completely different fields. So some years ago, some colleagues, quantum opticians, realized that the physics is pretty similar. Now, if you tell me what's the relevance of this, you see, that's one of my main motivations and why my talks create some rebellion from colleagues. Because nobody has to say why you do something or you create something. You know? When you paint something, You like it or you don't like it. You don't like it, you leave. You like it, you watch it again. See? So the essence of creativity in science is like that. You see, I find it funny. BC, black hole. Hawking radiation appearing in the structure of a BC. So you communicate fields and then you gain. This is the way. If you don't believe that analogies have value, I can tell you plenty of things. But I like one that is related also to my field, quantum optics. Light. Light. You see, and I go here and I tell you spring, elasticity. What has to do a spring with light, right? It turns out that Maxwell, when he developed the equations describing electromagnetism at the end of the 19th century, wrote this completed Ampere law and everything. Then came Dirac and said, we are in the time of the quantum. What about quantized light? He quantized light, and he realized that the most clever way of quantized light for creating the concept of photons was to associate harmonic oscillators, that means springs, mass, to light. You see? And if you tell any quantum optician,
already Planck had very similar ideas.
That's right.
Already when he
that's right. Only that
Planck
Planck just proposed the association between energy and frequency, but had not a single idea of
yeah, he didn't have an idea of
quantum, right? As you know, and
then
then
he used mathematical.
That's right. And then Dirac. So let's say if you tell a quantum optician, from the first chapter of any book in quantization of light, how I see light nowadays, I take any point of space around the source, and each point of the space has infinite harmonic oscillators, each of them with frequencies ranging from 0 to infinity, and each of those frequencies with two directions that are associated to the concept of polarization. See? So that's the way we see it. So light, quantum light, for a physicist, is just nothing else that each point of the space, that is the concept of a field, of a quantum field, is associated to infinite mass and spring with different values, you see, and we see these oscillations and this splitting. When it interacts with matter, we see also. So you see, don't tell me that associations are not useful. Dirac was able to associate springs, mass, and elastic things with light. See? And nowadays there is no way of understanding light, no way of understanding photons, and no way of understanding atoms, and the famous interaction of matter and light if it is not in terms of harmonic oscillators and springs and masses. So that's the origin. That's why I give a lot of value to this association between different fields, and that's essentially quantum simulation for us. Okay. The second is again another one, a little polemic, especially if you are a little expert in these topics, because I work a lot in these fields. Is because you can study phenomena that are difficult to access, or some phenomena that are absent in nature. Again, we come to the story of the forbidden or unphysical. See, and this is even more subtle. An example of complex conjugation is radical. It's just impossible. It's so impossible that nobody has done it, and nobody tries even. There is no lab in the world trying to make a complex conjugation. They would be fired immediately. But there is a lab in Germany that 2 months ago has implemented my proposal of how to fake the complex conjugation. So this experiment was done in Germany a couple of months ago. In this case, it's more subtle because in 2007, I published a paper in Physical Letters on how to make that a single trapped atom, in this case a charged atom, is a trapped ion, imitates the behavior of the Dirac equation that is a relativistic quantum dynamics. This paper was implemented. I collaborated with a group of Innsbruck of Rainer Blatt, who is also one of the leaders in the experiments of quantum computing and quantum simulations. And together we figured out how to implement it in the lab, and it's a Nature paper in 2010 where this was done. What was, yeah.
You may be getting to this later in your punchline, but I want to be able to see the endpoint a little.
No.
So when you say that someone in Germany has done an experiment that fakes, so I want to try to get you to be a little more precise, simulates or fakes or imitates an operation of complex conjugation, which is a forbidden operation. Now, does this experiment show that the laws of physics are not what we thought they were, or does it show that certain forbidden things, in fact, that we thought were forbidden or allowed, or is it because it's really an imitation and not really exactly complex conjugation, that it's just something a little different, or what is it exactly? The last thing.
In the same way, as I said, that's what I like the story. When I mentioned the story of the movie, it's really because it helps. You see, it's in the same way that you see Spider-Man falling incredibly and suddenly at 10 centimeters of the floor stops. This is there is nothing aerodynamic. There is nothing, no way to justify it. It's just wrong. That this is physically wrong. However, you see it and you say, oh, of course, it's a movie, science fiction. This is just special effects, right? It's the same thing that the people did in Germany. They follow our recipes on how to imitate artificially something. So let's say each time you observe, they did it with photons, with quantized light. Each time they observe the photons, the information they get from the photons is as if they were making a complex conjugation. But because the recipe is done like that, so the recipe is done in such a way that when you observe, it looks like it is doing something wrong. In the same way that when you go to the movies, you see, you don't believe that Spider-Man did that, right? You know that it's science fiction.
So what are they doing? They're imposing a basis on the wave function and then performing the conjugation relative to that basis?
I mean, it becomes technical. I'm sorry, then I have to answer technical. I wanted to avoid this technicality. Our technique of creating, simulating or imitating forbidden operations in quantum physics is based on a mechanism of embedding, what we call embedding quantum simulators. Instead of using the available Hilbert space of the system, you use an enlarged Hilbert space. So when you use an enlarged Hilbert space, you have room for cheating and for making this thing. But when you make the observations, you don't see this cheating. It's like behind the scene. You see, and you only see as if it is breaking the rules. But in fact, if you look the complete picture, you will see the same fundamental laws.
So the obvious way to achieve this is to make a subset of the Hilbert space.
Exactly.
And you're doing a superset of the Hilbert space.
You use a superset to observe a subset. In the subset, you break the rules. In the complete set, you never break the rules. I think you got the point.
Enrique, I'm not sure I should tell in advance what you are going to talk about.
No,
but it's essentially you consider complex space as a real space, as a space over reals. And then you introduce another complex multiplication in this real space.
Sure.
Yeah.
That's right.
So that's
it's in the same way.
Yeah.
I mean, let me give you another example. I think Nathan Weaver mentioned also this in my talking.
So it's like a tensor product with another
that's right.
number.
Nathan Weaver mentioned, for example, the complex. It's like if I tell you I studied engineer, by the way, before physics. No? So I consider myself also an engineer. So when I studied, that's right. No, complex. Why? Because I studied electrical engineering, and you use complex numbers. Then my teachers were saying things, abusing of the language, complex, and then the complex current and the complex one. I said, come on, nature is not complex. It's just that complex numbers fit pretty well. And at the end, when you want to extract the information, you take or the real part or the norm. It's the same speed, but in the quantum level. So you abuse of the possibility of the mathematical possibility of your system, so that the complete set always respects the fundamental laws. But when you take the partial information, it looks like it is breaking something.
Would there be any way to accomplish this operation physically?
The true one.
Given an arbitrary qubit, to separate it out, to say, here's a qubit, I now want a qubit where the real part of this goes over here, the complex part goes over here, absolute value.
That's what we do. That's what we do. So we said, as he said, we associate the real, so let's say what is called the real and imaginary part of a complex number are just real numbers.
Yeah, it's a realification followed by complexification.
Exactly. So you extend the Hilbert space such that when you observe a partial information, you see something absurd. But when you see the whole picture, it's always the same quantum mechanics. So this is imitation. So when I was accused a couple of times by colleagues, but you are using a trick. In fact, nature is not. Of course, do you think that if not, I would be. Everything upside down, right? that's the goal. But here, in the case of the Dirac equation, is more subtle, because when we did this theory and the experiment ran, you see, as I said, a non-relativistic system was imitating a relativistic system, which is also, so you see, Newton laws imitating Einstein laws. It looks weird, right? But this is what we did, and the experiment was showing that. The funny thing is that when we published those papers, some colleagues wrote us and told us, you know, the Dirac equation you were imitating is wrong. Because if you check these textbooks and you check my articles, we have proved that these properties called Zittel-Bevegung line paradox are just fake. Nobody has proved that this phenomena exists except in the textbook. So I started a debate with colleagues, and at the end I was very happy, because I said, look, so it could be that all that we were doing was, that's the beginning of our game. I said, okay, so you say that the Dirac equation is wrong at this level, fine. Then forget about what we said and just accept that we were imitating fundamental laws that are absent in nature, or physics that is absent in nature. It's not forbidden, but it does not exist. So when you observe the relativistic electrons, the experts were telling us that relativistic electrons do not do what you do in your model. I said, that's fine, then perhaps we are just imitating things that do not exist in nature. Then we started the game of the impossibility. Say, okay, if we are faking things that do not exist in nature, what about imitating things that are really forbidden in nature? You see? So it's a subtlety that I just wanted to share with you, because I will skip all the technicalities, Andre, if you allow me to skip, because I was giving you too much information. I cut my talk completely. But you see, my point is that everything that we are doing. Sorry?
You can write formulas, Enrique.
No problem. Yeah. I will skip some slides and I will show you the formulas if you want. But you see, then my point is that by working in quantum simulations, we are at the point, at this very moment, of believing that the difference between what you imitate, what is false, what is real, what is correct, what is forbidden, what respects the fundamental laws but is not appearing in nature, is very subtle. There are a lot of subtleties, and we don't know very well where we are in this moment. Reality is not my issue, as I said before. The third argument is this, of course, the relevant one concerning beating classical computers. There are some problems in quantum mechanics associated to the description of materials, of quantum chemistry, of quantum field theories, that are just impossible for classical computers. You see, we work in that, so we have several proposals of how to make simulations of condensed matter, quantum chemistry, quantum field theories, and our goal is really to simplify the computation. The fourth is the contribution to the quantum technologies, and the fifth is the one that I am mostly criticized, but I don't have to give any explanation to anybody. But this is why I do physics, you see? Because some people wake up one day and say, I'm not happy with reality, you see? And when you are not happy with reality, you have two choices. You disappear, or you create. And you create.
Drugs.
This is what
Drugs.
science right?
Drugs.
That's right.
It occurs to me that if you could do this in the real world, in some kind of physical operations, this would be an extremely powerful method of error correction.
we are into that. So Andre was indirectly requesting to be technical. I will jump to the technical issues, but I will show you, because as I like to defend the way ideas arrive. So we started working in this creating the quantum theater of impossible physics just because we like it. And I will prove you, if you want to be technical, that to fake complex conjugation, is the most powerful tool to extract useful information in scalable quantum computers and in scalable quantum simulators. And you will never be able to get relevant information about scalable quantum computers and scalable quantum simulators if you don't use this imitation of impossible physics. You see? But I will go to this very soon. So just let me be a little formal, just to show you. He was speaking about what is called circuit quantum electrodynamics, where you use superconducting qubits, like in D-wave, in this case flux qubits, coupled to quantized electromagnetic fields. In this case, in the 1 to 10 gigahertz, it's very technical. Trapped ions is another field where we work intensively. It's just using quadrupolar fields in Paul traps to confine to the ground state of the motion these charged particles. And this is also one of the strong candidates for quantum computing and quantum simulators. In the case of quantum photonics and this quantized light is also very promising, and of course neutral atoms trapped in optical lattices. And at this very moment, colleagues around the world are just mixing all these technologies to try to get the best. But if you want details, I can tell you.
What do you mean by an optical lattice?
An optical lattice is just two propagating plane waves that when they cross against the other creates the concept of a standing wave. And that in this standing wave, you create potentials that when you put two level atoms, due to the coupling to the light, they are trapped. So let's say they don't fall. And then they are pulled down more or less to the ground state, and you create a lattice where in each of these wells you have the qubits, because the two level atoms behave like the quantum bits. And then you use additional laser beams to operate on them. In fact, the first impressive quantum simulator was created there. It was this famous Nature is one of the most cited, I think the most cited paper in quantum optics, in fact, in the history. It's a Nature of the 19-something, where I was working there, by the way, in Max Planck Institute for Quantum Optics in Garching, and Ted Hensch, who got already Nobel Prize, and Immanuel Bloch implemented ideas of Sirac and Soler, as usual, to reproduce in a completely banal thing like neutral atoms trapped in these wells. They imitated a phase transition between what is called a Mott insulator to a superfluid.
What time period was this done in?
Sorry?
Time period.
Of the?
Like what year? What?
It's in the late 90s.
Oh, okay. This is already old stuff then.
Relatively.
It is. We are. You and everybody is here because of that paper. We will not be discussing this issue without that paper. That's one of the key issues. So everything related to quantum simulations exists at this moment because of this paper. So this paper was the motivation to say it works. In neutral, think it carefully. In neutral atoms with classical laser beams imitating a phase transition of materials. So people consider it as a historic result where you merge condensed matter with quantum optics. Condensed matter and quantum optics never merge. See, and that's more or less the relevance of this paper. So
It would be good if you send me a link, we could post it on the site.
Sure.
Well, I feel embarrassed that I'm sorry, I've never heard of it.
Yeah,
But I've been out of physics for a long time, so.
No, I have too many things. It's a long story of quantum simulation. This is one of the key. I was lucky to be there when this was done, so I got all the internal insight. I just want to mention, before entering into the technicalities of the complex conjugation, that I will want to please you, but let me just give you two examples, because I like this historic approach, because I think you understand better things. So I asked myself some years ago, what was the first quantum simulation? By the way, it was not that one of Bloch and Hensch, in my opinion. It was done by Dave Wineland in NIST, Boulder, Colorado. It's not Texas, but it's Boulder, Colorado, right?
It's flat.
That's right. And then, by the way, Dave Wineland got the Nobel Prize 2 years ago, together with Serge Haroche, for quantum optics. In fact, they got the Nobel Prize, Haroche in Paris and Wineland in Nice, because they were the first to prove, just to see everything that I say is very consistent, to prove that the quantum harmonic oscillator exists with all its properties. Only that Dave Wineland did it with a trapped ion, a trapped charge atom, okay? In these Paul traps that I said. They confined it, cooled down to the ground state, and started to move, and it works, the quantum mechanics. And Serge Haroche did it, with what? With light, quantized light. So he was the first to prove that the quantized harmonic oscillator describing the photons of light, in the case confined in a cavity, microwave cavity, in the 50 gigahertz. This is I studied all his papers, so I know absolutely, and the Wineland also. These are two fields that I have studied my whole life, so I know all the work of them. They proved that the harmonic oscillator in the quantized version existed. That's beautiful. It's a Nobel Prize 2012. And I discussed with Dave Wineland recently, and he agrees, because I told him, you did the first quantum simulation. And he thought later, he said, you are right. You're right. And why? Because what he did with the trapped ion, I don't have the paper here, he proved that a single trapped ion behaved exactly as an atom in the presence of quantized light. Right. So that's that. If you follow the literature, you see, and then at that time, nobody said that's a quantum simulation. It was not the time. Nobody said, are you beating classical computers? Nobody. People just said, wow, single trapped ion imitating an atom in a cavity. What has to do one with the other? But that was his work. And then these are just the figures of this is of Jeff Kimball's or Gerhard Rempe in Germany, and that is a typical cavity of Paris, or of Garching also. And this is a typical setup of Innsbruck. There are several trapped ions for quantum computing and quantum simulations. This Hamiltonian, if you're familiar with math, is nothing else than the James-Cummings Hamiltonian. Is considered the simplest Hamiltonian describing the coupling of quantized light and quantized matter. The sigmas, Andre was asking, are just the Pauli operators, the A and A dagger are just the creation and annihilation operators of the harmonic oscillator or of quantized light. It's the same. But you see, there is only one. I said that they were infinity. How can it be that we only use one? In the late 50s, here in the US, great theorists were working, making this model, and they created, James and Cummings are just family names, and they created this model. In fact, they said this model does not exist and will never exist. We just use it because we are theorists making calculations. 15 years later, other people, Dan Kleppner in MIT, Herbert Walter in Germany, and Serge Haroche in Paris, who got the Nobel Prize, discovered how to make it. And it was done in a cavity, and it's a whole story of what is called cavity QED in quantum optics. But in this experiment in trapped ions, as I said, they imitated this James Cummings model. It's written here in the language of trapped ions. And I always like to give the example that this is the first quantum simulation for one fundamental reason, just to see that I'm not claiming, I don't want that you agree with my view, but I wanted to give a complete view of this spirit. Try to think it carefully. What is the relevance and why you would want to imitate the James Cummings model of cavity QED that we knew everything? At that time, we knew everything about this model. You want to imitate it and fake it in a single trapped ion. And you tell me, what's the difference? The answer is nothing. It's the same. Then, with the eyes of this century, you would say, why to imitate if you have the original works? You know everything in the original. Why you want to imitate something that works pretty well? I was alive and doing science at that time. Nobody asked that question. You know what people did at that time? They enjoyed the result. They enjoyed the analogy. They enjoyed the connection with these two different fields are connected. Wow, cool. Others said, I don't like it. Then do something else. It's very easy. But you know why I want to present this example? Because when Dave Wineland copied the Hamiltonian of this coupling, they were not just saying, oh, I copied a partial property of cavity QED. They start to play with their lasers, because for building this fiction, it's a fiction, they had to use lasers. It's very technical. I can tell you the derivation by heart of this, no? Because I started with this, a very beautiful physics. And when they did it, they had to use lasers with different frequencies, acousto-optical modulators, Lamb-Dicker regime, dipolar approximation, vibrational rotating wave. It's a beautiful theory, see? You do it. And then they said, but we are faking it, right? With what? With laser beams. What about if we change the frequency? You know what happened when they changed the frequency? They created another interaction that nowadays is called, not James Cummings interaction, it's called anti-James Cummings interaction. You know what happened with this anti-James Cummings interaction? It does not exist in nature. Does not exist. Nobody has ever been able to see that a two-level system is coupled with a quantized light.
Because creation and the annihilation changed.
Exactly, Andre. See, because people said you cannot increase the energy of the atom and increase one photon or one excitation in the field. And when I was educated in this field, you can check the books of Haroche, Nobel Prize people.
This contradicts
that it tells you that it
right?
contradicts the conservation of energy. This is wrong. Sorry, this is wrong. You know why? Again, I'm sorry to be technical. This is a time-independent Hamiltonian. It takes one line demonstration that any Hamiltonian that is time-independent conserves energy. And we should abandon this mistake to think that the energy of the whole is the sum of the energy of the parts. You see, when you have coupled systems, the energy of the total system is almost never the sum of the energy of the parts. The James Cummings is
no one in their right mind would write something like this. Sigma plus times A.
That's right, that's what I tell you. I will say two sentences that are true and agree. It's not a polemic. Huh? The previous one, things perhaps are, these are not polemics, are standard things. This exists in nature. Two-level atom coupled to quantized light. This does not exist in nature, but it does not violate any fundamental. Both things are true. See? And why we tend to think, like you were saying, oh, it is creating energy from nothing. In the books, in the textbooks, it's written this. In the books that people are studying even now. Each time I give this talk, there are students or colleagues raising their hand telling me, and I have to explain again, because it has been overlooked historically, and I was educated like this. I was educated to say this violates energy. Does not violate energy. I'm sorry. It's a time-independent Hamiltonian. Take the Schrödinger equation, you write one line, calculate the expectation value, and it does not violate energy. Now, Dave Weiner did it, you see? And this is called, in the language of ions, James Cummings, anti-James Cummings, or in the language of ions, red Seidman excitation, blue Seidman excitation, because of the change in the frequency of the laser, you see? This is a pure copy of the cavity QED. This is an invention, a creation of an artist in the lab out of a copy. Okay? So you copy, then you change. That's what I meant. And I didn't mean that Beethoven was just copying. It's just you start by minor things and then you say what else and what else and what else. Now, some people would tell me, because this happens, tell me, okay, that's fine. They created this Hamiltonian. What for? You know what for? Check physical letters. 1995. Sirac Soler paper. The origin, that's why we are sitting here also, the origin of quantum computing. At the same time, Peter Shor developed his algorithm. At the same time, or some years before, David Deutsch proved the existence of the quantum Turing machine. And at the same time, Sirac and Soler said the first quantum architecture for quantum computing should be trapped ions. And you know, they created the first control knot for the quantum regime in this paper, and you know what they needed to create the first control knot. So the first control knot for a quantum computer, James Cummings, anti-James Cummings, James Cummings, anti-James Cummings, and so on. So it was impossible to create a control knot with the knowledge at that time with only the James Cummings. It was important, the existence. So you see, you imitate partial information. When you are bored with imitation, you create something that does not exist. The next step, you create a quantum computer. Okay? That's an interesting message for the young people and for the way you do research. Okay? So that's more or less the message. The second example I wanted to give you, before going to the technicalities of the complex conjugation, is what is another, in history, another relevant quantum simulation. Nature 2004. The origin of what? Circuit quantum electrodynamics. The origin of how superconducting qubits are coupled in a non-local way inside a coplanar waveguide cavity made by superconducting technology, cryogenic temperatures, 10-20 millikelvin, superconducting qubits imitating artificial atoms of two-level systems. Wow. Each of these charged qubits that was proposed at that time for a two-level system of superconducting qubit, you need billions of Cooper pairs controlled coherently. So billions of Cooper pairs were imitating a two-level atom, you see? And the Yale group, Rob Sholkoff, Steve Gavin, Alexander Blais, and others developed this concept of the James Cummings model. So if you check the paper, look, Nature 2004, 10 years only, they created a field that is the origin of what? Of T-wave, the origin of quantum simulators, the origin of all the efforts in NASA, Google here, of Santa Barbara, John Martinis, and so on. The paper Nature 2004, the only result in that paper is that they were imitating what? The James Cummings model. Again, at that time, I was the first in the planet, being from quantum optics, that started to work in this field, because I saw the whole story coming after, and all my colleagues at that time, including the big shots in the field, were telling me, why you start working and wasting your time and energy in this field? And I was puzzled, and I was asking all, I prefer not to mention the names, but all the top quantum opticians at that time, why you are so skeptical? And the answer was, because it is the same James Cummings model that we are used to. There is nothing new. We will not discover anything. It's the same physics. 10 years later, at this moment, I can tell you that this field is creating much better and more interesting quantum optics than all the original setups. Why? Because of what I was, sorry?
These guys are using, there's an interaction between the microwaves. The microwaves are part of the system. And what does the quantum optics of the microwaves are relevant to understanding how this is working. So I'm not able to visualize how that works.
I tell you, as I said, this is imitating the James Cummings from cavity quantum electrodynamics. Then the question would be, what is a cavity? What is a two-level atom? The cavity, in this case, is coplanar. The capacitors behave as mirrors, you see, with a certain reflectivity. If you see these arrows
above and below, we have superconducting containment sheets.
That's right. So you see the arrows are the electric field. If you see the structure of the arrows that go in this sinusoidal, is because they are imitating the first excited mode of the standing wave. So this is standing wave in the cavity. This is you have the first mode, the fundamental mode that is like this. This is the second one. This little thing in green, like a T, if you see, or like a little square there, like a little loop. The two dark things are Josephson junctions that are introducing the nonlinearity. The green parts are called superconducting islands. Each superconducting island has billions and billions of Cooper pairs. The question is, how can it be that billions and billions of Cooper pairs can imitate a two-level system? The answer is because the Josephson junctions are nonlinear devices that allow for those values just the cross of one Cooper pair or not. You have a reservoir, you have the Josephson junctions, and you have the superconducting islands. You put it at 10 millikelvin to reach the quantum regime, and you can prove that with a DC voltage, a DC line, you can administrate 1 billion. This is the surprising thing. Again, it sounds polemic, but it is the truth.
So
you know what is a superconducting qubit? Is 1 billion in the superconducting island, or 1 billion plus 1.
Right. So now these things are operating at about 10 gigahertz, which means they're about a centimeter.
1 to 10, typically 5 to 7.
So they're on the order of 10 or 20 millimeters in size.
The length is about 2 centimeters.
Yeah. Okay. Yeah. So right. Okay. Got it.
So I just want to make sure I understand your use of the word imitation here. If you take like a magnetic, like a loop of current, right, and then you talk about an electron spin, would you apply the word imitation to the fact that the phenomenon associated with a single loop of current and the fact that you can put it in a magnetic field and it will tend to align, and then you have something going on with the spin? There's an analogy there, but is that what you mean by imitation, or is there more to the idea of imitation?
In this case, I think you left in the moment when I said that at this very moment to say how close is something to the real model or how fake is the imitation is very subtle. It will depend on the example. In your example, is in between. But what I would really call an imitation, just to simplify, is when you have a predefined mathematical model that you associate to some physical description, but it's predefined. See? And this predefined model, let's call it, for example, James Cummings model. It's a simplified model, because the James Cummings is 2 levels in the atom and 1 harmonic oscillator. You know how many levels has an atom? Infinite. Infinite. So when I say 2 levels, obviously I am simplifying, because I can in the model. It's a model. Just to finish, the cavity, how many modes has a cavity? Infinite, but I'm just using one. This is the James Cummings. It's a simplified model that describes correctly a certain sequence. When I take this and I try to force another system to imitate that model, this is what I call an imitation or a simulation.
What I'm trying to, because I think people have been doing things like this for a while, maybe not to this degree or in this realm, and I'm just wondering what the word imitation connotes above and beyond. We can model this system with such and such an equation. I mean, normally I would see something put out there and I say, we're going to model this system by such and such a Hamiltonian or whatever, and you're using the word imitation. I'm wondering what extra, or is it the same thing as when you use the word imitation, is that the same as saying such and such a system can be modeled in this way, or we can construct a system that, such that this equation is a model for it?
Both. So that's what I meant. I made a general statement before, because at this moment everything is valid. Just to give you an idea, there are some people trying to use quantum simulators, for example, for solving a mathematical problem. But I said a mathematical problem, and before I said a physical model. What is the limit? Or the physical model exists in nature. The Dirac equation apparently does not exist in nature at the level I use it for a quantum simulator. Then some people tell me, this does not contradict fundamental laws, but it does not exist in nature. And you imitate that. What are you imitating? So for me, I am just imitating models. I take a mathematical model and I reproduce it in a physical system. But this mathematical model can be associated to another physical system, can be associated to a possible physical model that does not exist in nature, or it can even be something that contradicts fundamental laws. It's very general. At this point, we don't have. If you go to the literature, you will never find the definition of quantum simulation, and that's what I'm trying to do.
So when you, so just let me try to ask it one more time in a different way. So when you're using the word imitation, are you bringing any more to the notion that when we've always talked about modeling a system or constructing a system that such that this Hamiltonian or whatever describes that, or are you just bringing the word imitation into the discussion because of your desire to connect it to the arts? In other words, you want to make connections outside of science, so you're bringing in this other word, imitation, to do that, but you're not really doing more than science. Anyone who's been just a scientist all these years would never use the word imitation.
My answer is yes, 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 yes.
Okay.
All right. But just to complete a little bit, there is no difference in our community between imitation and simulation. In fact, this is one part of my talk that I don't know if I will be able to mention. In fact, there is no difference between imitation, simulation, emulation, virtualization. There is no difference at all. Our community is pretty ignorant about the subtleties of what means to imitate. It's pretty ignorant. What I'm doing is a pedagogical effort to define, and that's why it gets polemic. No, you check the last review of quantum simulations in Nature, you will be very disappointed. There is nothing like an effort. You don't know what they mean. They assume. Until one day I was giving a talk for the general public, and there was a computer scientist raise their hand and tell me, how you make the difference between quantum simulation and quantum emulation? Then I said, wait a second, I go home, I studied, and then I came with my stuff. So I am the first raising the issue of what should be the difference between emulation, simulation, and combining this with imitation. Our community is pretty ignorant, it's pretty unaware of these subtleties, differences, and so on. You see, so I'm just coming with a proposal. And just to answer directly your question, I don't see the difference between imitation and simulation, but I see a difference between simulation and emulation. And this is what I will.
What about the word modeling, which is the word as working in the engineering field, we always use the word model.
That's right. In my version, I use the word modeling, as I said, when I observe, I make abstractions, and I make a model. A model for me is always, at this level of work, is a mathematical, abstract description that I extract from observations and I use to predict and to test. When it doesn't work, I correct my model. Until it works. When it works, I say, okay, it's a nice model. When I use this model and I apply it to another system, I call that quantum simulation.
But an imitation really is more the system that such that the model applies to that. So an imitation is more like an implementation as opposed to
implementation of a previously extracted model from another observation.
Yeah, I'm just trying to get the word straight in what they're referring to. Yeah.
But you're right. As I said, go to the literature and you will be very disappointed. I'm just making the effort. I have not written still a review of this, but I plan to do it because I need to clean this. So I go to the issue. Analog or digital, I think I don't have to convince you of the relevance. My big point is that our community in quantum is separating these two fields. We are trying to unite them in a consistent manner, but this is a technical issue that I don't want to enter now. But this is, I come to your point, you see. In my last talks, I am constantly bringing this. I gave a talk 2 days ago in Berkeley, which was very interesting also, in front of the community of trapped ions and the community of superconducting qubits. And it was very interesting. There was a colleague who wrote a paper in Nature commenting another paper a couple of years ago, and he put in the title Quantum Emulation. Then you read the paper, and it was emulation, simulation, imitation, simulation. then it's a thread of years. Then I profit and I asked him something that was obvious to me. Can you tell me what is the difference between the? Nothing. I just didn't want to repeat the same word, and I was just switching. See? Of course, it was obvious from the paper that it was like that. Then I said, let me give you my view. I have put there some definitions of simulation and emulation. I've not invented them. You go to the textbooks or to Wikipedia, and you will see. And I give you a brief example because I find it's useful. See? You take a black box. I keep my Dirac equation. I want to imitate the Dirac equation. I put an input. I measure the output, I check the output, and I said, wow, this is the Dirac equation. And then now what is inside the black box? You open the black box, and you see, wow, this is not a relativistic quantum dynamics, but somebody has been trying to imitate all the parts of the Dirac equation. You really see the effort to imitate the quantum dynamics. And you say, that's why when I measure the output, it works. This is what an expert would call a quantum simulator. Another case B, you open the black box and you say, where the heck is the Dirac equation? I only see cables, atoms, photons, there is nothing, nobody's trying to, but the output looks wonderful. You see, this is a quantum emulation, as simple as that. So essentially, emulation is when you care much more about the precision in the results of the emulated system, and simulation when you care more about imitating really the internal structure. Though this is very radical because I was reading the literature of computer science, and you enter into technicalities that you never stop. You know, there are cases where people say, I don't know, it is more, it is both. It is none, it is both, and perhaps Andre, you wanted to comment.
Yeah, let's continue. Just continue.
That's right.
And more technical.
That's right, no? Yeah. And then the just to go to the technicality of the to finish, no, of the complex conjugations that were moving your hearts, it is here. You see, essentially the concept is this embedding quantum simulator. You can check the paper. It's a Physical Regulators 2013. Formally, we claim that embedding quantum simulators is the first formal effort to merge the two fields of quantum computing algorithms with quantum simulators, and I will tell you why. Don't have what to sign, but you see, this is the world of the normal, usual quantum mechanics. You have wave vectors describing quantum states, and you have unitary operations. It's rather simple mathematics. See, unitary operations are everything that you can do with interactions in quantum mechanics, and the description of the quantum states are wave vectors. If you impose mathematically this operation called complex conjugation, mathematically you can define it. You apply, you get complex conjugation. As I said before, and I don't want to enter again into this debate, this is a forbidden operation for a physical system, not for the mathematics of quantum mechanics, but for a physical system. What we do, we use an enlarged space. In this enlarged space, the wave vector is described in an enlarged one. So if this is a qubit represented by a Hilbert space using two complex numbers, this is a wave vector with 4 complex entries, where each of these 4 complex entries only use the real part. So here you have 4 real numbers, there you have 2 complex numbers. 2 complex numbers are then a 4 real parts, so this is no problem. In this case, when you make this mapping, you use that's our proposal, we use a clever mapping such that the complex conjugation that is forbidden in nature, in the true quantum mechanics, turns into a unitary operation in the enlarged space. That's the thing. You see?
So let me just write this what on the board. Maybe someone you.
Well, is the blackboard an enlarged Hilbert space?
Yeah. So what is this? So it is essentially that you start with the Hilbert space, say H, and then you take H like a real space, and then you eventually just multiply it over reals by another complex numbers.
Yeah.
So this is what your enlarged space is.
That's right. If this is what I understand better, that's right.
So what is the actual procedure for entanglement?
I show you now so you can have a look to this paper. This is the citation of the experiment. You see, it's April 2014, where this group in Alexander Samait in Jena did this. If you see experimental simulation of charge conservation violation of electrodynamics, the charge conservation violation is also another forbidden operation. It's technical. It's very easy to speak difficult. Very easy to speak difficult.
Yeah, so
What is hard is to pass the message.
But going back to complex conjugation, my question: how do you actually
That's right.
specify the basis?
How
do you find?
That's
the
why
basis
I
if you
have
can
it
do
here.
complex
I have it here for you. So you
Okay.
see, the initial space there, the wave function, is made out of two complex numbers. You separate a real and imaginary part. If you see here, you see, and then the complex conjugation operation just transforms into this.
Yes, Enrique, but to separate the complex and the imaginary part, you already need to have some basis in this space. So that's my question. You need to have a basis. Like, for example, with the complex numbers,
Yes.
in order to separate normal complex number, you need to have a basis. This basis is just one in complex numbers. If you multiply a complex number, this one by something else, then separation into this imaginary part will be something completely
I
different.
think the trick is that it'll.
Yeah, so
that he just
what basis
picks one.
do you specify physically?
Whatever.
Yeah. How do you choose the basis? That's
The way I want,
I,
the way you want.
if he
There is
chooses,
nothing mysterious about choosing a basis.
if he chooses an arbitrary basis,
Yeah.
at the end of the process, that basis will cancel out.
Yeah, I hope so, but you need
No.
this basis to start with.
That's clearly, as you realize, I didn't want to enter into the technical, but I understand the motivation of the question. Quantum mechanics can be formulated in operator language without needing
Yeah,
of a basis.
invariant, yeah.
When you want to approach to a given experiment, obviously you need to define a basis. The basis is typically defined by the physical system. If you use a two-level atom, you use the ground state and the first excited state. You use a harmonic oscillator, the 0 photons and 1 photon. What is undefined is the global phase. The global phase can introduce changes, of course, in the structure, in the complex structure. A global phase is never affecting any observation. You can change the global phase the way you want, you will never change a physical prediction.
I
So
know
once the physical system defines the basis for your experiment, there is nothing.
Yes, but as soon as you multiply by a phase factor,
Yeah.
you change the notion of real and imaginary part.
I repeat my sentence.
Mhm.
You can change the global phase as you want, it will never produce difference in the prediction.
Well, this is like bookends. You will first do the transform to go into the larger space,
Mhm.
perform some operations within that larger space, and then perform the inverse transform to go back into the ordinary. And that, as long as the anti-transform is subject to the same arbitrarily chosen basis as the original, the whole thing cancels out. Now, what we kind of hope here is that we don't have crazy things happening like imaginary numbers turning into real numbers and vice versa. But that's a detail. In principle, whatever basis you choose for the initial transform will be canceled out when you do the anti-transform.
Yeah, I
So,
also hope so.
as I said, I see your point, Andre, but let me tell you, as I said, this would
I
need really.
don't want us to get stuck in that.
No, but as I said, I'm here just to answer these kind of questions. The ones that you probably alone you will pass 3 months, I can tell you in one sentence.
Yeah.
If you start with any wave vector and you put a certain global phase,
Mhm.
physics, quantum physics, is about predicting measurements. Measurements are typically associated to single events that are statistical or to expectation values. Whatever you put as a global phase in the beginning will never appear in any observation or measurement. Never. Whatever. Even though it looks like, because of course you are multiplying by a phase. A phase is a complex number. And then you see this phase entering in all calculations. When you compute predictions of observations, this cancels out. This is the essence of it. And here is the same. It's only more tricky because of course you are worried about the mapping. This mapping, of course, depends on a basis. You choose a basis that is given by the physical system. You put the global phase, and then you continue. And unfortunately, there is no magic. At the end, this global phase never enters into it. Even though you see it moving, it never enters into it. Think it carefully. The same thing for electrical circuits. You use complex numbers. There also you have a global phase. when you measure a voltage, this will never depend on the phase you chose at the beginning. It's the same thing. Yeah? So let me just advance what you see. So let's say the complex conjugation, as you see in this new enlarged space, turns into something that is physical, because even though this operation, as I said, is not unitary, in fact it's an antilinear operation, here in this enlarged space is just a composition of Pauli matrices which can be associated to unitary operations. To see the value of this, because this is pure math, really, because what we do when we do theory is to try to approach to possible experiments. So if you see this equation that is called the Majorana equation, I see that you are more or less familiar with math. If you have a look to this equation, it's exactly as the Dirac equation in 1 + 1 dimensions, only that instead of having here the wave function, I have put the complex conjugation. The fact that I put the complex conjugation, if you see, forbids me. I will write the Hamiltonian here. It's C sigma x px minus I mc squared sigma y. Here I have upside, and here I have upside complex conjugate. So I cannot factorize. I cannot tell you that there is something like a Hamiltonian, a Hermitian Hamiltonian, because I cannot factorize. I have psi and psi complex conjugate. The usual Dirac or Schrödinger equations are of this character. When you put the complex conjugation, you break the whole unitarity of quantum mechanics. And we proved in this previous paper that this equation that is violating quantum mechanics can be imitated by another equation that respects quantum mechanics. So this is the imitation of this encoded and physical quantum dynamics. And this is what the group in Germany did. So they were able to use the true quantum dynamics of a true quantum system imitating a quantum dynamics that is just contradicting the fundamental laws. Okay? So I will follow to see. Here is the story that I was telling you earlier. So quantum mechanics is about computing expectation values. And here you see that the expectation value of an observable in the usual space, in the initial space, can be associated to the expectation value in the enlarged space in such a way that these global phases are not affected. You see? And in particular, in this is a figure that appeared in the article I like a lot, because in quantum mechanics, at this level of first quantization, you have 3 discrete symmetries that you see all over in the literature. It's complex conjugation, charge conjugation, time reversal. I know many colleagues also raise the hand and say, of course, I can make a time reversal. Time reversal is a forbidden operation. It's not unitary. See, sorry. I mean, we can repeat it as many times as you want. These 3 discrete symmetries are operations that are forbidden by nature. You cannot apply them in a given experiment on a wave function that you don't know. In this paper, we proved that with this systematic enlarged space, you can produce physically or with unitary operations these 3 discrete symmetries in a consistent way, following a quantum dynamics. You see? So that's you have to be careful. I don't know how technical you are. It's very, very subtle. Charge conjugation is a forbidden operation in first quantization of theory of field theories, and it's an allowed operation in second quantization in quantum physics. It's very, very subtle, so I don't want to enter into this because it becomes technical. I just wanted to end my talk coming to the central point of this concept of embedding quantum simulators. No, it's in this paper. See, and that's what I wanted to tell you, that we started just with this artistic approach of just enjoying what we produce, and we discovered something that is very deep. And I can be technical, but let me just make the sentence that you get the point. One day, D-Wave, John Martinez, Dave Winan, whoever will be the scalable quantum simulator. Really, the example I gave at the beginning, 100 spins with this horrible 2 to the 100 dimensionality, and imagine that it is perfect, it's doing perfect stuff, really perfect. So you can make everything perfect. You don't believe it? Me, I believe it, yeah. But it is challenging, right? Then, in this very moment, I or you will say, okay, wonderful, we did it. Nobel Prize, enterprise, 100,000 people employed. And then I come, or you, and say, please, I ask you a physical question about your system. Compute me the degree of entanglement of this massive entanglement. The degree of entanglement, measure the entanglement of this device. And then John Martinez will tell you, wonderful, but what do you need? And the answer is, just give me the whole density matrix or the whole wave function of the system. I told you before that you need 2 to the 100 complex numbers. You need to measure them in the lab. This is impossible, not because of physical laws. It's just impossible because the time you need to measure this can be 100 years. It's impossible. The numbers are too huge. The techniques are slow, so nobody will be able to measure. So even when we will have the quantum computer and the quantum simulator that is perfect, there will be physical questions that you can ask that nobody can answer. Unless you use what? The simulation of the complex conjugation that I propose. Why? Because in this paper, you see a PRA 2005, some colleagues, Andrea Osterlo and Jens Sieber, discovered that most of the ways of measuring entanglement for n qubits, you see n qubit entanglement monotones from antilinear operation, require physical or mathematical operations that involves antilinear mathematical operations. Antilinear, as I told you before, is unphysical. Everything that is antilinear is unphysical. Mathematically, you compute on the paper, but it is impossible to do it in the lab. And then we discovered that for being able to implement this measurement of entanglement for 100 spins or for n-qubit systems, you could use our enlarged spaces with this trick of being able to imitate a complex conjugation. If you see many of the definitions of entanglement monotones, I didn't invent this. If you check we started to work in this field in 2011, but you see this paper is from 2005. It was always known that measuring entanglement is associated to complex conjugation, but nobody saw that it was a forbidden operation. Why? Because people asked for full tomography of the system, compute on the paper or on these computers the complex conjugation, and thought it was fine. But there will be the moment very soon, in 2, 3, 5 years, where you will have a beautiful scalable quantum simulator and you will not be able to measure entanglement. And then when you use this proposal of the embedding quantum simulators, that is implementing the dynamics with a complex conjugation being simulated inside, instead of needing 63 observables, you would need just 6 for the 3 qubit case. 3 qubit case. I'm speaking about 3 qubit case. For the 4 qubit case, imagine, I'm speaking about 4 qubits, you will need to measure 255 observables. With our method, you may need 54 for this kind of entanglement monotone. And for this, what is called, I mean, it's a technical thing, the extended or generalized concurrence entanglement monotone proposed by Wouters, you see, instead of needing 255 observables, you will need just 2 observables.
Wouters' formula is actually determinant, right?
That's right. If you check the paper of Wouters,
I just read it today.
No, but that's a good point. If you check
it,
what is the definition of concurrence for Wouters, it's nothing else than the absolute value of psi sigma y for the first qubit, sigma y for the second qubit, and you will see the beautiful complex conjugation here. Many years before we started with this data, and we just discovered that they cross. You see? So, as I said, how you do this for the measurement of Wouters?
But if you compute it in the basis in which the psi is just a matrix, like it is say a times 0, 0 plus b times 0, 1 plus c times 1, 0 plus d times 1, 1. Then it is just something like bc minus a d, right?
Exactly.
Maybe complex conjugation on top.
Exactly. But it comes from this expression.
Yeah.
It comes directly from this.
Of course. This
You see,
expression
but you see, you have done it with your hands
determinant,
on a classical on a classical
on a
device.
piece of paper.
That's right. And when you have 2 to the 100 numbers, to do this on a piece of paper, you need to ask the experiment, give me the 2 to the 100 values.
Right.
If they give it to you, even if they give it to you, probably you will have a hard time computing, because I don't know any computer that allows for a vector. Have you ever heard of a computer, a vector of 2 to the 100 complex numbers? I've not heard that yet. Okay? So even if, but they cannot give it to you, because nobody can do an experiment to measure 2 to the 100 complex numbers. Okay? So given that it is impossible, if he produces it's impossible for you, nobody will be ever able to measure entanglement, even in 100 qubits, okay? Which is not really that impressive. And what we are proposing is that instead of using 100 qubits, you use 101 with our embedding technique with the enlarged Hilbert space. And automatically, the number of measurements that you need is strongly reduced, and then you can get information.
Yeah, so this tensor multiplication by R basically increases your dimension.
But you see the key issue. What is the key issue of our proposal of embedding quantum simulators? The access to fake or imitate complex conjugation in a true experiment. So it is the possibility of faking the complex conjugation in the true experiment that allows you to answer a physical question that otherwise you cannot answer. And as other colleagues were observing, what is the mathematics behind this result is that we are merging two different concepts. So our embedding, our enlarged space, is nothing else than a seed, a hidden quantum algorithm that you put from the beginning, such that for any time t of the evolution of your quantum simulator, you extract efficiently the measure of entanglement. See? So this merge of, again, I call it merge because people say there are two different things. But I mentioned at the beginning that for Feynman already, quantum simulator and quantum computing were very similar concepts. With the history, they have been separated because of specialized research. I think it is time to converge back and to reproduce these things in an efficient way. And with this, I finish my talk because it was already too long.
So you gain a huge amount of information if you can extract the entangled state. A lot of the algorithms, they reduce the final answer to something you can measure, but if you can just measure the entangled state without collapsing it, is what you're saying?
No. Again, these are. I didn't want to enter into those technicalities because I understand that you have read a lot. Everything that is measured in quantum physics is collapsed. Forget it. Everything is collapsed. Everything. There is nothing like a system that you say it collapses, and you have to. I didn't want to enter into the technicalities. Each time I say one observable, not 200, one each observable, formally needs infinite measurements. Quantum physics is like that. You like it or you don't. Any expectation value formally needs infinite. Of course, you cannot. Then what you do some, as many as you can. And what you do, certain error. That's it. This is what you. But each time you make a measurement, you collapse the wave function. Again, I don't want to enter into the metaphysical issues. You collapse, I speak collapse. Nothing collapses. It's just mathematics. It's just mathematics.
Okay, but what would you actually get if you had a quantum computer with 2 to the 100 qubits all entangled and you ran this with your...
This is not an expectation value. An expectation value is the average of an observable that is Hermitian. There is nothing like Hermitian. This is just a mathematical. The definition of concurrence is a functional. It's not a measurement. It's a functional of matrix elements of a certain quantum state. It's not an observable. That's why it needs full tomography. You take the whole elements of the density matrix, you calculate a functional, that's a measure of entanglement. Entanglement requires the knowledge of everything. I didn't invent the concept of entanglement, it is like that. When you have 100 spins, you will need 2 to the 100 complex numbers. I'm sorry, nobody can do that. Nobody. So how can it be that you have a perfect quantum computer and you ask physical questions that are interesting and it cannot be answered? This is absurd. Right? So the embedding quantum simulator concept aims at solving this problem by just enlarging the Hilbert space by a factor of 2 in the dimensions.
So I don't pretend to be following all the details here, but what are the implications of the reduced number of observables? It sort of feels like you're getting something for nothing, because this imitation, as you pointed out, you're not really solving that forbidden equation. You're solving something that resembles it or imitates it in some way. And now I'm seeing this 54 observables in the enlarged space, 255 observables. So what's the implication?
That's a good point. Of course, the experience in life shows us that you cannot win everything. No? So when you win something, you lose another thing. So as I said, it looks like magic because suddenly you needed too much and you needed too less. It's the same game of algorithms. You see, so you prepare the system, the enlarged space and the embedding prepares the system from the very beginning. From the very beginning, you make this mapping and this enlarged space such that each time somebody asks you, I need this function I call concurrence, the system is efficiently prepared to give it back this number out of fewer operations. It is prepared only for that. If you ask other things, it becomes just impossible. Yeah. This is the basics of algorithms. You build algorithms to simplify a specific calculation. And who is doing this calculation? Not you. The experiment is doing it. That's the trick of the embedding.
Now let me get back to the question I sent you in the email. Because at certain point you need to measure operators that do not compute. How do you do it?
That's right. You don't do it, or you do it and they have errors.
We have errors.
There is nothing.
We have just have to live with errors.
That's right. That's right. I mean, because errors, in the way you express them, because of the non-commutation or anti-commutation of observables, is just the ABC in quantum mechanics. That's the origin of the probabilistic theory. So the most exact theory that we have developed for describing microscopic nature is a probabilistic theory from first principles. This comes, for example, from the incapacity of measuring for any time t with maximum precision two observables associated to non-commuting momentum. This is
because you measure two Pauli matrices that anti-commute.
But Andre, that's the origin of the EPR paradox. Of course, there is no paradox. It's the origin. It's the fact that you have to separate two-level systems that are entangled, and then when you measure in the set basis, you say, oh, I have these correlations. When you measure in the X and Y, then you find contradictory things. There is no way in which you can understand this with classical probability. You need to use the superposition principle of the Hilbert space vectors to understand this. And what is the essence of this? The non-commutation properties of sigma x1. So there is nothing mysterious, and there is nothing different from the usual quantum mechanics. So that's the origin of the probabilistic interpretation.
So you can answer this quickly, but every person that's given a talk that I've seen here has at some point stated quantum mechanics as one of the two fundamental laws of the universe. And they speak of quantum mechanics as classical mechanics as a limiting case of quantum mechanics, but somehow quantum mechanics is really foundational.
Yeah.
When I studied quantum mechanics in graduate school, we used Landau and Lifshitz, who at the very beginning of his book says, classical mechanics, I keep coming back to this, classical mechanics is not merely a limiting case of quantum mechanics, but it is required as part of the formulation of quantum mechanics, because we define a measurement to be the interaction of a classical system with a quantum system. And I actually really liked that. You know, I liked the idea that classical mechanics was not simply a special limiting case of quantum mechanics, but it was just very foundational, you know, equally foundational. And I think it helps you escape a lot of the nutty paradoxes that, you know, people are still putting out there. And I'm just wondering if you're familiar with Landau's statement there, or the way he formulates classical mechanics as being essential, and whether you agree with it.
I also had the pleasure to study the books of Landau, Lifshitz, and the famous mechanics, which is the smallest, by the way.
Oh, really, yeah, that is so fabulous.
Beautiful. Just to be short, I don't know any paradox in quantum mechanics.
Okay.
I don't know any.
Okay.
I'm sorry.
That is short.
I don't know which books are you reading or which colleagues you are consulting, but I don't know any.
Well, for example, let's take the Schrödinger cat one. You know, I frequently see the Schrödinger cat paradox that somehow this cat is not, you know, until we like open up the door and look at it, you know, it's not known whether it's alive or dead. If you look at Landau, you simply say there's you know, once the interaction between the
you see, I was the first to propose how to engineer a Schrödinger cat in many systems. I invite you just to shorten the discussions to have to read. If you Andre, you can ask me by email. There is a beautiful 2-page article written by Chris Fuchs and Asher Perez in Physics Today, where the title is Quantum Mechanics Needs No Interpretation. And they describe the example of the Schrödinger cat and proves you very easily in 3 paragraphs that there is absolutely no mystery, even opening, not opening, it's just standard.
All right, well, I'll need to read that, but I've seen articles discussing the Schrödinger cat fairly recently that somehow act, you know, they speak as though this cat is in the superposition of being alive and dead until we open the door and look at it. And I said, that's just absolute nonsense.
Yeah, so again, I just to answer, because as I said, I don't run from this, but it becomes very technical and very long. There is, in my opinion, and in fact, it's not my opinion, it's following the Copenhagen interpretation, the standard, very radical and pragmatic. Quantum mechanics doesn't make any statement about wave functions, linear superpositions,
Right.
or Schrödinger cats that are based on entanglement. Quantum mechanics only makes statements about measurements, be probabilistic for single measurements, or expectation values for averaging, and nothing else. So linear superposition for me is mathematics. A linear superposition extended to multi-part system is entanglement. Schrödinger cat is mathematics. I don't make any statement about things that are not field measurements. The cat, this debate on the paradox exists because you are reading the linear superposition in the Hilbert space. But this is not a measurement, this is mathematics. Physics appears in quantum mechanics when you measure. When you measure, there is no cat there, there is all dead or alive.
Well,
That's my
if you read the original Schrödinger cat paper,
Ich habe das auf Deutsch gelernt.
which is in German,
Of course. That's what I said in German.
yes. Schrödinger prefaces the description by saying, it is possible to construct quite bizarre and unrealistic experiments. And he goes on to describe the diabolical mechanism with the cat. Schrödinger himself thought that this was absurd, and the reason why he wrote the paper describing the cat was to emphasize the absurdity of
Extending quantum mechanics to the macroscopic world. That's the main motivation of Schrödinger.
Copenhagenistic interpretations of macroscopic objects.
So you're saying superposition is actually like the complex numbers in electrical theory, right? So it's just a mathematical.
Well,
You see, our community in quantum physics is strongly divided in many axes. One of these axes is the people that want to read physics where there is no physics. I am not in that community. In that community is the people working in Bell inequalities, paradoxes, interaction without interaction, seeing a photon without observing it. This, if you read those papers, I'm sorry, I am out. I will never accept a paper like that, and I don't accept papers like that. This is metaphysics. I do physics. I do physics. I don't do metaphysics.
in the world of practical quantum computing, people who are actually trying to build stuff that's going to actually be used by actual people to like actually pay their electric bill. You know, engineering of entanglement is an ongoing thing. Superposition is a routine method.
As I said, this we can discuss in private. See, when I am here, I try to be professional. I have also my metaphysics.
Yeah.
But formally, when this discussion gets tough with colleagues, with experts, I always tell them, can you tell me a single physical observation in an experiment or in nature that contradicts a prediction of quantum mechanics? If the answer is no, let us shut up. No, let us shut up. Because physics is about describing observations. It's not about inventing things that we want in our religious lives or in our aesthetic lives or in our metaphysics lives. But physics is about describing observation. There is nothing in nature nowadays that makes me think that there is something wrong with quantum mechanics. This is what I want? No. I would want quantum mechanics to fail. Why? Because I am an ambitious guy. I want to live enough to see a breakthrough in history. but professionally, there is nothing like a paradox or an observation that contradicts quantum mechanics. If you think the opposite, show me the paper.
The mean life of a scientific theory is 7 years. Quantum mechanics is long past its due date.
It's interesting when, in your mind, before you open the box to look at the cat, you really don't know if the cat is dead or alive, right? So in your mind, it could be either. So superposition.
It's not the way I've seen it written.
Yeah, it's, in a way, superposition.
I see it very commonly written.
Is a very
that
useful
somehow the
concept.
cat is in a superposition of alive and dead, and so
No,
I think the reason that happens is because people view quantum mechanics as the fundamental law of the universe, and they're ignoring Landau's advice
Yeah.
that classical mechanics is needed as part of the formulation.
I follow your approach. No, so it's not it looks contradictory at all. I do believe, and in fact, Michael said, in my group, I am very, very strict with this. At this very moment in the evolution of the intellectual interpretation of physics, I only know effective models. So when you tell me we have to design a Chrysler car, man, if you start to use quantum mechanics, you are putting our lives in risk. Of course, it's fundamental in the sense that there is a large set of observations and predictions and modeling and predictions that need this beautiful essence of quantum mechanics. When you tell me the ground state, the stability of the electron in the ground state of the hydrogen atom, if you insist on classical mechanics, then of course we are creating paradoxes. But quantum mechanics, when I go to sleep and I think in quantum mechanics, I am happy because I know that when I will wake up, the stability of the universe will be there. The universe will not be stable if we insist on classical mechanics. The stability of the universe comes from the essence of the Hilbert space modeling of nature.
For the exclusion principle.
That's right. This is crucial. It's crucial. See, atoms will collapse if classical physics is true. Will collapse. The electron. You see, the electron has acceleration. Accelerated charges radiate. The electron in the hydrogen atom does not radiate. That's why it is stable. So don't tell me quantum mechanics brings me clarity, brings me understanding. I don't have anything quantum mechanics. I would want that it breaks, but this is my personal problem. But it works perfectly up to now. I hope it stays.
Let's give Enrique another
Can you post your slides?
You post your slides, right?
Yeah. Okay. I will send Andre my PDF.
Did you read the other two papers that Shirley has published in response to EPR?